Hi, welcome to this introduction to digital logic. Analog logic is what you're doing with motors. This is digital logic. It's the basis behind computers. Everything we study in digital logic can be traced back to Claude Shannon. This is a picture of him. He had about 30 unicycles in his garage when he died in 2001. So what we're going to do is simulate logic gates inside software called logic simulation or Logisim. We're going to go over the Logisim user interface. And then at the end you're going to build a robot that follows a flashlight. We're going to go through each of these behaviors right here one at a time. All circuits consist of inputs, and we list our inputs over here and then our outputs. In this scenario we're going to have a child asking the parent questions, and the parent's going to say yes or no, and then the child's going to obey or disobey. Now, if you've ever had a 2-year-old, they don't pay attention to the parent.
No, Daddy. No.
So this is the parent's response after the child's talked to them or not talked to them. In the 2-year-old's case. Click the mouse on it once and then it changes to 1. You click on the mouse on it again and it changes to something else. A 2-year-old's behavior is more like a constant. No, 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 no. So this is the symbol for a constant. Typically we think of 0 as no and a 1 as yes. So 0 is false and a 1 is true. And this is the 2-year-old saying no, no, no matter what. So the parent's just sort of not connected to the circuit, right? The circuit consists of an input and an output, and here the input's a constant. The 2-year-old just says no, 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 no. Here we're hooking the parent up to the child, and the child's very disciplined and just follows the parent. If the parent says no, the child doesn't do it. If the parent says yes, then the child does it. So switches just poke at a well-behaving, well-mannered adult. Now what we're doing is we're introducing our first gate. Instead of having just a switch and a wire and an LED, what we have is our first gate right here. So a NOT gate is like a really evil teenager. The teenager asks the parent if they can take the car. The parent says no, then they take the car. The teenager asks the parent if they can take the car. Parent says yes, and instead they get a ride with a friend. You can't tell what's going on with a really evil teenager. Now a really good teenager is an AND gate. This teenager is aware they have a mom and a dad. They ask both of them if they can take the car, and only if both the mom and the dad agree does the teenager take the car. If they disagree, the teenager doesn't want to cause a fight, so they don't take the car. So this is an AND gate. True and true equals true. True and false is false. False and true is false. Now this is a bad teenager or an immature teenager. They ask both mom and dad as before, but in this case, if either parent says yes, then they take the car. Here they ask the dad, mom says no, but dad says yes, so they take the car. Then the parents go off and fight. Here they ask the mom says yes, the dad says no, and they take the car, and the parents go off and fight. And if they both agree, then it takes the car. So this is a bad, immature teenager. This is called an OR gate. This or this, then this. Now this is how circuits remember. This is how our brain works. And you can wire one of these up and try to get it to work if you want. Okay, so here what we're going to do is build a light following robot. Here's our inputs. We have a left. This is a flashlight sensor, and when it's 0, it sees no flashlight. We have 3 of these flashlight sensors, one on the left, one in the center, and one on the right side of the robot. So this is the person out here looking at the robot. The robot's chasing them. And so this is the person's left arm, center, and right. So if there's no flashlight, then what we have the robot doing is stopping. If this sensor goes on, that means the flashlight's aimed at it. Then it turns the left motor on, so that this motor turns and the robot basically goes forward and turns towards the right. This motor is off, so it pivots around that motor and turns to the right. So that's why the left motor's on when it senses the right. Now if it's in the middle, it does both. Now if the two flashlights are used, if you got kids and they both have flashlights and try to confuse the robot, the X's mean unpredictable behavior. It means we don't care what's going on. We're not trying to support that situation. If the left light sensor is activated, then it turns on the right motor. This motor turns on, the robot spins in this direction, like that, towards the left. The right motor's on, the left motor pivots. And then these other two situations down here, where we have three situations where we have multiple flashlights, we don't care. Now your assignment is to build this circuit and then either make it cheaper by removing one of these gates, or make it more expensive and make the robot move better in these unpredictable situations. And then turn in a circuit, just upload a circuit that works, that's different than this one.